It's a great pleasure to welcome Nicolas for today the third of his Eisenstein lecture series, or the fourth if you count the colloquium of Friday. So he'll be continuing his lectures on the Czech cocycles and hyperplane arrangements. Nicolas.
Thanks. So today I will switch from topology to more differential geometry. So the title would be differential forms on the symmetric space associated to SL and C. And so to first make the link with the subject I've discussed so far, remember that the whole topological construction started from the consideration of a certain Tom form. So topological construction started with a certain Tom form, and now the goal today is to describe a differential form representative of this Tom form. So we will use so-called Mattei-Quillen formalism to build this. To build a differential form representative of this Tom form. So that's and using this formalism, we will be it will be easy to transgress this Tom form, meaning to find a representative and therefore a lift in the long exact sequence, as I discussed in the topological setting. So to do that, let's take some notation that I will follow today. So in the whole lecture, V will be C to the n, and G will be the linear group acting on GL and C acting on C to the n, and K will be the unitary group UN. And so each time I have an element in G, then I will associate to this element an Hermitian form. Namely, the form which is obtained by translating the canonical Hermitian form by G. So this is an Hermitian form on C to the n. The matrix of this Hermitian form is a conjugate of G minus transpose times G minus 1. And the space of this Hermitian form, is an homogeneous space, which I will denote S. It is so G mod K, the space of all these positive definite Hermitian form on C to the n. So it is a G homogeneous space. It is not quite the symmetric space associated to SL and C. The symmetric space is a quotient by the real numbers. I rescale the Hermitian form, and so this is a symmetric space of SL and C. So eventually, that is a space I want to work with. So let me say what is the goal of the lecture. Now, the goal is to construct to construct two differential forms. First, a differential form I will denote phi, which will be of degree 2n, and live on S cross Cn, and a second differential form of degree 2n minus 1, again on S cross Cn, that are both rapidly decreasing in the fibers Cn. So in the fibers of the projection S cross Cn over S, and such that first phi would be a so-called Thom form, so associated to this bundle. So phi is a Thom form. Meaning that phi is closed and the integral over the fibers of are all equal to 1. And one important feature I forgot to mention, but very important, is that I want this form to be G equivariant, so G invariant. So in fact, I should add a G here. So I want this form to behave well with respect to the G action. That's it's not hard to build a Thom form in general, but the point here is to build it in a G invariant way. And so this will be the use of phi. Phi is a Thom form. And now how we will use psi. In fact, the interesting property of psi is that the Mellin transform of psi at 0, at s equals 0, gives a form which I will denote eta, which again is a 2n minus 1 form, but it will be only defined, it will descend on a form on X, a symmetric space, and it will be defined everywhere except at 0 on the fibers. It will be again G invariant, closed, and representing the fundamental class of C minus 0, so the fundamental class. And so that will be that will be the differential the differential form representing the class that we have dealt with topologically. Okay, we remember we started was from the Thom form, and we transgressed it in the long exact sequence to a form that was a 2n minus 1 form on Cn minus 0 and a G equivariant form. So that's the goal today. And to achieve this, I will use, as I said, the Matthaei-Quillen formalism. So I won't give a course on the Matthaei-Quillen formalism. I will just describe what are the Matthaei-Quillen forms and gave a formula, and try to give a sense why it's an interesting formalism. And so the Matthaei-Quillen forms will be associated to will be obtained by considering the principal bundle G over S, which I recall is G mod K. So this identifies G with a K principal fiber bundle. And there is a G, of course, there is a natural G action of G on itself, and the natural G action of G on the quotient G mod K. So it's a G equivariant bundle. and it's naturally equipped with, there is a natural connection form on this bundle. So a connection form is a one form on the total space. So here this is G with values in the tangent in the tangent space to the fibers, which is the Lie algebra of K. And I want this to be invariant under the action of G on the G side and the action of K by the adjoint representation on the Lie algebra. So because it's an invariant form, you can move everything above the identity point, and so this is the same as a linear form on the Lie algebra of G. Tensor is the Lie algebra of K, and it's a K invariant linear form, and this is the same as home K of GK. And now the connection, if you think of it like that, it's just the projection. So theta is just the projection, the orthogonal projection with respect to the Killing form. So you can just remember that there is a natural G invariant connection on this principal bundle, and
connection flat.
What?
Is the connection flat as well?
No, the connection is not flat, and it has a curvature, an associated curvature form omega that that is this time a two form on G, again with values in the Lie algebra of K, in the tangent space to the fiber, and this is a curvature form of this connection.
Yeah. Okay, and it doesn't vanish. I mean, every connection has a curvature form, but
yeah, no, it doesn't vanish. Yeah, I mean, yeah, it doesn't vanish. And now so this is only related to the bundle G over G mod K, and now we want to put in the picture the V space. So I will now consider the associate bundle, which is G. I will explain the definition. In fact, this is the product of G by V quotiented by the natural K action that I will describe on G cross V. And this is the bundle over S again. And the action here is just given by GV K is equal to GK K minus 1V. So I take a right action. And again, this is a G equivariant bundle. G acts on this just by acting on itself, G, and with no action on V, and it acts on S by the standard action. So the way you should think of it is, of course, it's somewhat analogous, but as we just discussed, it's not flat, but it's somewhat analogous to the bundle we consider in the first lecture, meaning EG times GV over BG. But now we keep track on of some continuous feature of the group. And again, there is a standard metric defines a metric on V. which is G equivariant because G doesn't act on V here. So it gives a G equivariant metric. And when you have such a data, then MataEquivalent produces for you a form which is a differential form representative of the Thom form associated to this bundle. So here is the, and so it's a Thom form, and I will describe by giving the formula. I won't describe the formalism that leads to this. It will take me at least maybe more than 1 hour. But in the end, the formula is quite suggestive, and I will explain how you should think of it. So let me first give the formula. So it's a Thom form, but as I said, it's not a compactly supported form because this is not very canonical. But it's a goal. It's a Thom. Once you fix a metric on the fiber, you can consider the corresponding Gaussian function, and so it will be a form that is rapidly decreasing, like a Gaussian in the fibers. So there is this term along the fiber, and now the rest of the expression is that you sum over subset ij of the interval 1n, such that I and j are the same size. Here you have some signs I will describe later. I prime is a complement of I inside 1n. Yeah, jj prime. This is another sign. And then you have some determinant of a partial. So omega is a curvature form, so it is a matrix in. I mean, it's an element of the endomorphism of K. So it's a matrix that, and you can take the determinant of this partial of the partial matrix determined by I and j. And then you have dz plus theta of z. Theta, it's a differential form with values in K, and K again acts on V. So it's again a matrix. So you can apply it to a vector in V, and take the wedge product along the coordinate I prime, and here dz plus theta z bar, and you take the K product using j prime, and you inverse the indices. So let me look at the main term of this, just to understand what it means. So first, to recall what I've said orally, that I prime is 1 over n minus I, and the same for j. If you take multivector xi, so wedge xi prime, then it's epsilon of ii prime x1 wedge xn. So this is the sign that I defined. And now what is the main important term to understand here is the case where there is no contribution from the connection. So assume, for example, that you were only working on V and forget about the group G. Then what you get is let me add some space here. What you get is 1 over 2 pi to the n, the Gaussian term, and now here you remember only the term that comes from the dz. And so what you get is Z1. So now the only term that counts is a term where I and j are empty. So you have I prime is equal to 1 to n. So the first term is dz1 up to dzn. And then the second term, it's you bar everything and you go the other way around, because I said that it's g prime star. So it means that I go from dzn star bar up from dz1 bar. And so when you look at this is just the volume form in the fiber multiplied by the Gaussian. And what you want to do is to have a deformation of this form in the fiber, so that it varies as a differential form on G, and the global form, the family of form, is still a closed form. So U is a deformation of this on the fiber above the identity, such that it is closed. So if you try to find a way to deform this over the space G mod K and keep a closed form, then you get this. I mean, that's why that's what Matthias Quillen managed to do using the connection form I have just written. So I won't say much about this. I want more to explain how to use these forms to in relation with what I have described in the first two lectures. But I want you to remember two important things. So three important things. So it's a deformation of this of the canonical form in the fiber over the identity. There is a Gaussian behavior along the fibers, and apart from this Gaussian behavior, you have only polynomials in here. What you get in the z variable are only polynomials, and what happened here and inside the theta are coordinates that comes from the base. Okay, but in the fiber you have really polynomials times a Gaussian function. So in particular, it's very rapidly decreasing.
In the SL2 case and SL3 case, can you write down these forms explicitly?
I will write down this form explicitly after a change of coordinate that is that will be that I'm doing right now. Okay.
Mm-hmm.
But only in small dimension, because it's quite it's become quite involved. I mean, the compact form is this one. So now let's consider forms not on the bundle G cross V mod K, but on S cross V. And for that, note that the standard action turns the bundle, which I will denote by E, which is just S cross V, into a G equivariant vector bundle. So now it's a trivial bundle, but the G action is not trivial because now I'm considering the diagonal action on E. Okay, G acts both on S and on V. So there is a diagonal action here. And the map phi identify this bundle. So in a way, it's a way to trivialize the bundle which just considered before, G cross V mod K. You trivialize it using this map. And if I'm not mistaken, if you change G by some K on the right, then you will have the same class on G cross V mod K. So this is a way to trivialize this bundle, and this map is G equivalent. So it's a G equivalent trivialization of the bundle we just considered. And in fact, we will work with this trivialization. So let me define now. Let small phi, the pullback of U. So it's an element, it's a 2n form on E, which is G invariant, okay? And it's closed. And I will denote psi, the pullback of so here X is the radial vector in the fiber. So in complex coordinates, it's Gi delta I plus Gi bar delta I bar. So it's the radial vector field in V. And the radial vector field, just to connect with what we have done before, the radial vector field is an infinitesimal version of the multiplication by in the fibers. Okay, so when I'm doing I'm doing this operation that I don't know how to I don't remember how to say it in English, but when you put the radial vector field in, when you feed U with the radial vector field, then it's an infinitesimal version that what we were doing with the multiplication in the fiber. So we'll come back to this, but that's the relation with what we've done last time. And so note that this radial vector field is invariant by K. Okay, so again, this form psi is a G invariant form. Okay, so both phi and psi are G invariant form. Phi is closed. Psi, there is no reason for psi to be closed. It's rapidly decreasing, of course. Both are rapidly decreasing. In fibers, and since it's G invariant, to compute the integral along fibers, we can just stick to the base point over the identity, and so we can compute using the formula just over the base point that the integral over the form is 1. That's why we put I over 2 pi to the n. So phi is a Thom form. So that's the first goal. So that's really what achieved by multi-equivalent formalism, of course. We just have made a slight change of coordinates. And so now we will look at the second part of the goal. What happened with the Mellin transform of psi, and what is the relation with phi and all that. So that's the second part, a closed 2n minus 1 form on x cross Cn minus 0. And now we will put into play the multiplication in the fibers. So pick a scalar S, a positive real numbers. Now it's not an integer, but it induces a multiplication map in the fiber, which I will denote like that. So multiplication by S in the fibers. And by definition of psi, we have that if you take the differential of the pullback of psi by this multiplication map, so you have psi is a differential form on S cross V, you can pull it back by the multiplication by S in the fibers, then because psi was obtained by yx of phi, then it is equal to S times d over ds of the pullback by S of phi. So this is a little exercise in differential geometry, but this is really the same as what this really follows from the definition, and from that I will prove something which will be important for us. So let's call it a theorem. It's not very deep, but it will be important. That if you consider the integral, which I will call eta, which is, in fact, it's minus the Mellin transform, if you want. So now I tell exactly what means Mellin transform in that case. You pull back by S the form psi, okay? So if you want, you are when S tends to what you do when you do that is to change your Gaussian by a multiplication by S. So there is still so you have fixed symmetric, but there is still something which is not canonically defined. Is how much is how is your Gaussian? So it could be you could multiply your Gaussian by some scalar, and so here you are looking at all the Gaussians from the situation where S tends to infinity. It means that you have concentrated everywhere on only the term in zero are not going. I mean, inside exponential minus SV is V is non-zero, then it tends to zero very fast. So you have a Gaussian that is very thin. And when you go to zero, then you tend with something that is the identity that is flat everywhere. So you go from one to the other, and you take this expression, and I will say that this integral is convergent and defines a closed. So that's really the most important part of the theorem. Form. Yeah, one of the oh, let me say it that it's readable. It is a closed form in 2n minus 1 x cross. So it means that it descends on x, which is not a surprise, because if you multiply your form by your form in the fiber by a scalar, then it goes into the integral, and I mean, if you replace s by ts, then the change of variable tells you that you get the same expression. So it descends on x cross cn minus 0. So you erase 0 typically because you want your form to be rapidly decreasing at infinity, and it's G invariant. And this form, I already spoiled it in the introduction, represents the fundamental class of x cross cn minus 0. Okay. So that's so let me prove this this theorem. And the first thing is to check that the integral is indeed convergent. So, and for the convergence here, we can first look what happens as s tends to infinity. Then the Gaussian part gives you a factor of type exponential minus sz square, and these decrease very fast. On as long as you are away from z equals 0. So there is no convergence issue as s tends to infinity as long as you are on Cn minus 0. And now what happens as s tends to 0, then you have to look at the expression given by the Matta-Equivalent formula. And in fact, since you have killed using since you have taken iota of the radial vector field, you have killed the factors where there is only forms depending on the base. So there are factors depending on the fibers, and when you multiply by s, then they give you some s factor here, meaning that the form tends to 0 when s tends to 0. So the integral we are considering here is convergent also at s equals 0. So the form is well defined. And invariant by multiplication in the fibers, by scalar multiplication in the fibers, so that in the end, eta descends into a form on X, which is still, of course, G invariant. So that's the first part of the theorem, and now we have to compute the differential of this form, and that's where you will understand a little bit where comes the definition of psi. Let's compute d of eta formally. So by definition, it's minus d of this integral. The differential, since now we know there is no issue of convergence, so this is the same as minus the integral, and you apply the differential to the form. And here you have ds over s. But now we have said that the differential of s star of psi is equal to s times d over ds of s of phi, s star of phi. So the s here are compensate, and in the end you are just integrating from 0 to infinity d over ds of this, and so we know a primitive, and this gives that the limit as s tends to 0 of s star of phi minus the limit as s tends to infinity of s star of phi. And now, what happens when s tends to infinity? We are taking a Gaussian that is more and more concentrated on 0, but we are working on Cn minus 0, so we are away the 0 section. So this tends to 0. So this is equal to 0. And now what happens where this when now S tends to 0, so it's almost flat. So now the main term in the expression of multi-equivalent is precisely the term where there is no where we look only at what varies on the base. And what varies on the base, it's the main term where both I and j are of size n. And what you get here is, of course, I over 2 pi n, and the pullback of the determinant of the curvature form. So this is an invariant form on S, or in fact on X also. But okay. In general, this invariant form could be non-zero. So we want to prove now that in our situation, this invariant form is in fact 0. And this will be related to the property in the topological setting that the bundle, the Euler class of the bundle was 0. In fact, this differential form representative is a representative of the Euler class. So we could just say that it's exact, but in fact we will prove that it's identically 0. And now, so we could compute, but let me give rather a conceptual explanation of how to prove this very simply, and relate this to the flatness of some bundle. So the conceptual explanation is the following: we will use the so-called Weil trick. That invariant form on the symmetric space X corresponds by the so-called Weil trick. And maybe I should, Weil trick here to harmonic form, in fact, harmonic invariant form on the dual compact space. The invariant form on X are in fact corresponds to the harmonic form on the compact dual of X. But on the compact side, the determinant of omega represents the top Chern class, or the Euler class, in fact, but the top Chern class of a flat Cn bundle. So the determinant of omega has to be identically 0. So in the end, yeah, because it's harmonic, so it represents a 0 form. So in the end, by Weil trick, we know that our omega and our initial determinant omega is also identically 0. So
why does it become flat on XC?
Because because it can be G equivalently, equivalently, not G, it's a compact dual of G, trivialized bundle. So it's on here, so maybe I should rather, it's better with S, sorry. So S, the compact form, is UN cross UN mod UN. So it identifies with the group UN. And the bundle we are considering above is just isomorphic as UN cross CN.
Mm-hmm.
And so it's a flat vector bundle, and the curvature form of this bundle is 0.
It's because this unitary thing that SC is
that is because,
I mean, the main reason is because SC is UN cross UN, mod UN, and the bundle is also
exactly. UN cross UN is a compact version. In S is GLNC cross UN. So the compact version of this is so the complexification of GLNC is GLNC cross GLNC, and the compact form of this is UN cross UN. And now, if you write down US cross UN mod UN, it identifies with UN. So as a symmetric space, SC is just UN. Okay, and you have the trivial bundle. And the bundle we are considering is the trivial bundle on this.
Mm-hmm.
So that's the important thing is that now maybe I haven't said this, that now the invariant form, because we are on a compact space, are harmonic form, and so if the harmonic form were not was not 0, then the Chern form, the Chern class was not 0, and contradicting the fact that the bundle is flat. So it has to be really identically 0, not only exact. And coming back to the original space, we get that omega on the determinant of omega on S was identically 0. So again, that uses the fact that we are working with CN fibers. It will not be true if we use the SLNR and Rn vector bundle. Then the Euler class, the Euler form would be a non-zero class. So that's really the analog of what we discussed in the first lecture. That over Cn, because Euler class is a Chern class, then it's 0. So that there is one thing that we have not proved yet. It remains to prove that eta represents the fundamental class of X cross Cn minus 0. And to do so, we may restrict to the fiber over the class of the identity. So then we can compute everything, because then phi is equal to which is the same.
Can you actually explain what it means? What do you mean when you say it represents the fundamental class?
Oh, it means that it will so X cross Cn minus 0 is homotopy equivalent to Sn minus 1, and so it has a fundamental class, and the form is the closed form represents this class here.
Okay, thanks.
So again, you have to remember that what we are trying to do is to lift somewhat equivalently the fundamental class of Cn minus 0 to equivalent cohomology. So here there is a lift to of the fundamental class of Cn minus 0 to x, which is contractible, times Cn minus 0. So that has a representative that is now G that is really G invariant. It's not a G invariant form on Cn minus 0. This would be too much to ask, but it's a G invariant form on X cross Cn minus 0, which has the same homotopy type. Yeah. So now, what is phi? It's 1 over p to the n exponential minus. So I write everything now in real coordinates because it's easier to relate with sigma n. So in real coordinate, it's just this form. So now it's a coordinate in R2n, which I identify with Cn. Okay, and now the radial in these coordinates, the radial vector field is just the sum of xj dxj. So I can compute what the iota of phi, iota x of phi to get psi, and psi is just 1 over p to the n. So I still have the Gaussian factor here, and I have the sum from 1 to n, and each time that I feed my form with the vector d of del xj, then I multiply by xj, and there is the sign to be remembered, so it's this, and here the form times dx1 up to dxj that we forgot, dx2n. So that is my my psi, and now I can compute eta. I take the Mellin transform of this, and I will spare you with all the computation, but it gives you a gamma factor over 2 pi n of the same sum here, dx1, dxj star, yeah, the same differential form here, and divided by the norm, the square, the norm square to the n. And this is just the volume form of the sphere. Of normalized to a volume 1. So on the fiber, it really represents the fundamental class of Sn minus 1, and since it's G equivalent, we are done. So we are done with the proof. So again, what we have computed is a representative of the fundamental class that is G invariant, but not on Cn minus 0 itself, but on some Cn minus 0 times the contractible space that is G, that is X. So it's really, you see the analogy with what we have done topologically in the first lecture. And let me give some example. And that's the funny thing in this business, in fact, is that in the end, the only thing we will compute really is what happened. We will always go back to the situation n equal 1. So we have to understand precisely our forms in the n equal 1 situation. And the goal is to reduce to n equal 1. That's something I will explain tomorrow. So let's give expression for the form in n equal 1. So it seems very sad case, because then the symmetric space is just a point, and S is the positive reals. So, and X is just a point. And then phi is 1 over 2 pi exponential minus r square z square, r square dz dz bar. So this is really the volume in the fibers, and the correction terms to have a closed form when you vary on the base is just r square times z dz bar minus z bar dz wedge dr over r. And then what is psi? Is minus I over 2 pi r square z bar dz minus I square z dz bar. And eta is this expression, which is just in the coordinate z equal r, in the polar coordinate in the fiber, is just d theta over 2 pi, which we are not surprised at this point, since it's a volume form of the one sphere, and note that d theta over 2 pi is equal to 1 over 2i pi dz over z minus something which is d, I mean some exact term, which in fact is dr over r, which is exact on c minus 0. So this is the first occurrence from this point of view of the dz over z part, which made a crucial appearance in the description of the cocycle in the affine case. Okay, and there is another observation I want to make, which is also important, is that if you look in the eye how phi is, it has two components. It has a component that over, so if you fix one r, then it has a volume. It has a Gaussian. I mean, it's essentially it's. I mean, this first part here is the renormalized by multiplication by r of the Gaussian of the term form above just a point. Okay, and then there is another part which is psi. You see the psi here over the point r, wedged with dr over r. So the fact that phi is closed reflects exactly the property I described, that d of r star of psi is equal to r times d over dr of r pullback of r of phi. Okay, and in general, so this will be a general phenomenon that will be used on. We can make the Matta-Equivalent formalism work on and we have that on here the term form. Let me call it phi tilde, because I have added some one more parameter which is multiplication by, which acts on v by multiplication by r. Then phi is equal to a form which I will denote alpha, plus another form which I will denote beta, wedge dr over r, and r is the coordinate in the first factor, and alpha restricted to r times s cross v is just r phi but rescaled by r, and beta restricted by r cross s cross v is just r form psi restrict by psi. Maybe there is a sign mistake. I don't want to check now, but you see that therefore the integral that we have considered is just the integral from 0 to infinity of phi tilde in the R variable. Okay, if you integrate in the R variable phi tilde above here, then there is no contribution of alpha because alpha is constant in the I mean, there is no dr component here. So there is only the second part that occur, and the second part is precisely this expression. So in fact, I could have written everything in terms of term form, and that will be important in the next lecture. Oh, I'm running a little bit late. I just want to add the last thing, if this is fine, Henry. You stop me if this is a very last thing, is to relate this to Schwarz forms and veil representation, but I don't. It's in our situation, it's a very easy concept. So this form phi of m psi, which again belongs to this, in fact, we can associate to this form phi tilde and psi tilde. Sorry, it's not the same as above, which are forms on S cross V, so the bundle I denoted E, tensored with, so if you take form with values in the Schwarz form of V, and that are invariant under not only the group G, but the group G semi-direct product with V. So the affine group, if you want. And the definition of this form is just that, let's do it just for phi tilde of W, where W is an element in the Schwarz space. So phi tilde of W is now just a form on E, is by definition the pullback by the translation by minus W of the form phi. So it belongs to. And since I am running out of time, I will leave you as an exercise the fact that using this definition, in fact, we have that if you take GV, an element in this semi-direct product, then, and you put this semi-direct product acts on E, on S cross V, okay? And you can therefore pull back a form, and I will pull back the following form, GW plus V. So this is the action of G of the semi-direct product G times V on the space V, and this is equal to phi tilde of W. So this is just a very simple computation, but it tells you that this form phi tilde and psi tilde are therefore they should be thought of as test vectors at infinity with values. I mean Schwarz functions with values in differential form. And why is it important? So that's my conclusion. Importance of that. Because now suppose that L in V is a lattice. And gamma in G fixes the lattice L. Then you can form a theta series. Namely, theta of phi will be the sum over all the vectors in the lattice of phi tilde of psi. This, you see, I should say it like that. If you evaluate phi tilde at 0, you get phi. But now you take, instead of evaluating at 0, you evaluate it at all points of the lattice. You do an average, and it is invariant by the semi, not by G semi-direct V, but it's invariant by gamma semi-direct lambda, precisely because of this form of the formula here. Because gamma semi-direct L preserves the lattice. Okay, so it's invariant. And so you get a form, a 2n form on the quotient gamma of S cross V by gamma semi-direct L, which is exactly this quotient. So it's a 2n form on this quotient, and it's closed, and it represents a Thom form. Or a dual form to the zero section. So now that we have this test function, we are in good shape to do to really go into arithmetics, because we can average with any kind of lattice or Schwarz function at a finite place. So that will be the last part of my lecture, to use this test function as Archimedean test function. And this is very close to, in another context, Kudlai-Milson. Kudlai-Milson provide you test function at infinity to build forms dual to some special cycles. Here, that's essentially what we do, except that our special cycles are much simpler. These are zero section of this bundle S cross V. So, okay, I will stop here. Sorry for again being late today.
So thank you very much, Nicolas, and thank you also for ending your lecture with some homework for the discussion session of the afternoon. So we'll try to think about that. Are there any questions or comments?
Just a quick question. It was about your theorem. And so you defined the Mellin transform of this specific differential form phi. Is there a, but I think the way you've defined the Mellin transform as an integral, one can apply this definition to any differential form in this bundle. Is that correct?
Yeah. I mean, that's not me. That's really already in the multi-equivalent form. I mean, they transgress the Euler class of the bundle, and that's the way they transgress the Euler class in full generality. And the source of it, in fact, is the proof by Chern of the Gauss-Bonnet theorem. If you apply this kind of method in the tangent bundle, so first you construct the Thom form of the tangent bundle, and then you prove that you can transgress it in the sphere bundle using precisely this construction, this type of Mellin transform. Mm-hmm. And when you compute now once you have this transgression, then you can just check that the total integral of the Gauss form, which of the curvature form, give you the Euler characteristic using this transgression form. So that's how Chern proved the Gauss-Bonnet theorem, and Mattei-Quillen used this and put this in a more general framework, somehow in the general framework, and that's and now I take Mattei-Quillen and put in a very specific framework.
Good, thank you. Again, it would be, I mean, maybe in a later lecture, it would be nice to see this form explicitly. So this for n equals to 2, let's say, this last thing that you wrote down.
Yeah, I haven't. I don't think I will do it, because you'll see only the form for n equal 1 will be important. But if you want to see it, I can make some advertisement for my Takagi lectures when it's on my webpage, and it's written where the expression is written.
I see. Okay, great. So that's for n equal to 2.
N equal to 2. Yeah.
Okay, I'll check that. After
that, it's becoming a bit messy, and my point is really to explain that we can avoid computation by what I will explain tomorrow.
Okay, thank you. What time is the discussion session in the evening?
Oh, yeah, the
Or-
discussion session is at the CRM in Montreal.
Okay,
It's very,
okay.
again, it's a very informal thing, so it's not, I mean, yeah, it's not part of the international part of the conference.
Great.
So,
Thank you. Thank you so much.
Yeah.
Bye-bye.
Are there any other questions or remarks? Okay, I guess we're maybe Virginie, maybe you can stop the recording.